Module 1, Lecture B, Variables and Expressions. By the end of this lecture, you will be able to create variables that represent civil engineering quantities with meaningful names, use arithmetic expressions and built-in functions to compute engineering values, and apply basic type awareness to avoid common calculation errors. Engineering variables. Meaningful variable names. Meaningful names make engineering calculations easier to understand and safer to review. In civil engineering, names should clearly describe physical quantities such as beam length or concrete strength, so others can quickly recognize what each value represents. Clear naming helps prevent mistakes when calculations are shared and decisions depend on using the right information. Name engineering quantities clearly by stating the object, property, and when needed, the location or condition. For example, distinguish upstream from downstream drainage areas, dead loads from live loads, and dry soil density from saturated soil density. Concise, specific names reduce confusion and make calculations easier to understand as designs become more complex. Meaningful names in engineering calculations make each quantity clear before it is used, including its units and whether it is an input or a result. This reduces errors, supports better engineering judgment, and makes computations easier to debug and explain. In education and practice, clear naming turns calculations into a more coherent technical narrative. Python code. Meaningful variable names. Clear variable names make engineering calculations easier to understand and check. Good names should indicate what a quantity represents, its units, and its context, while vague names can make the calculation harder to follow. Define the beam span length as 6 meters using a clear variable name that includes both the quantity and its unit. This makes the value's purpose easy to understand in engineering calculations. The beam loads are defined as a dead load of 12.5 kilonewtons per meter and a live load of 8 kilonewtons per meter. The dead load is the constant weight the beam supports, while the live load represents variable forces such as occupants or furniture. Using clear names and units makes the code easier to understand and maintain. The total service load per meter is found by adding the dead load and live load, both in kilonewtons per meter. This gives one clear value for the load the beam carries along each meter of its length, with descriptive naming that makes the meaning and units easy to understand. For a simply supported beam, the maximum bending moment is found by multiplying the total service load by the beam span squared, then dividing the result by 8. The answer is expressed in kilonewton meters and represents the peak bending effect caused by the applied load. The output displays the beam span length, dead load, and live load using clear engineering units. These labeled values help confirm the inputs and make the beam loading information easy to understand. The example also reinforces the value of descriptive labels and meaningful names in engineering calculations. The code reports two key structural results with clear labels: the total service load in kilonewtons per meter and the maximum bending moment in kilonewton meters. These outputs make the units and meaning of the calculations easy to understand. The example highlights the value of clear result descriptions for communicating engineering calculations effectively. This example shows how meaningful variable names make engineering calculations easier to understand. It computes the maximum moment for a simply supported beam by combining dead and live loads into a total service load, then applying the standard beam moment calculation using the span. The output clearly labels the span, loads, total service load, and maximum moment, so the results are easy to interpret. Meaningful variable names. Use meaningful names in engineering calculations so quantities are easy to identify and check. In civil engineering, names should specify what is being measured, such as beam length, pipe diameter, or pavement thickness, especially when projects include similar dimensions. Clear naming helps others review calculations later and reduces confusion and errors. Variable names in engineering calculations should state both the quantity and its context so the meaning is clear. Terms such as load, stress, pressure, or area can be ambiguous unless they specify what they refer to, such as different types of loads or areas in a design. Clear naming makes calculations easier to understand and supports professional communication. Clear, consistent naming makes engineering calculations easier to understand, check, and reuse. Names should be concise but meaningful, showing the material, component, and quantity involved, such as distinguishing slab thickness from beam depth or soil unit weight from groundwater depth. This is especially important in team settings, where readable calculations support accuracy, professionalism, and long-term usability. Python code. Meaningful variable names. Use meaningful engineering variable names to make calculations easier to review. Including units in the names also helps prevent mistakes. The bridge dimensions are defined in meters, a span length of 30, a deck width of 12, and a pavement thickness of 0.18. These values describe the bridge's main geometry and support later calculations of material volume and weight. Using clear names with units helps keep calculations understandable and reduces errors. Use a concrete unit weight of 24 kilonewtons per cubic meter to estimate the slab load. First, find the slab volume by multiplying the bridge span length, deck width, and pavement thickness. Then multiply that volume by the unit weight. The result is the slab weight in kilonewtons, which is used in structural analysis and design. Clear variable names make code easier to understand. A vague name like size does not explain what the value represents, while a more descriptive name for the bridge span length in meters makes the variable's purpose clear and supports easier review. This example shows why meaningful variable names and clear units matter in engineering calculations. It prints key bridge dimensions including span length, deck width, and pavement thickness, each labeled in meters. Clear labels make the output easier to read, reduce confusion, and support more accurate interpretation. The code prints key bridge slab results with clear units: the slab volume in cubic meters, the slab weight in kilonewtons, and the bridge span length in meters. It also contrasts a vague variable name with a more descriptive one, emphasizing that meaningful names make code easier to read and review. This example shows why clear variable names matter in engineering calculations. It computes a bridge concrete slab's volume and weight using descriptive names that include units, making the code easier to check and less prone to mistakes. The output reports the main dimensions, slab volume, and weight, while contrasting vague naming with clearer naming to emphasize good coding practice. Descriptive quantity names. Descriptive quantity names make civil engineering calculations easier to understand by clearly connecting values to the physical elements they represent. Clear names help engineers see whether a value refers to something like length, strength, area, or force, reducing confusion in design work. This improves communication among engineers and other stakeholders. In engineering calculations, quantity names should state both what is being measured and its specific role. Clear names like bridge deck width, allowable soil pressure, design speed, or dead load distinguish similar concepts and reduce confusion. This precision helps prevent errors, especially in complex calculations that may change over time. Descriptive quantity names help engineers connect each value to its units, assumptions, and physical meaning, such as length, force, or capacity. This is especially important when combining information from different sources or checking calculations. Clear names make engineering work easier to review, debug, and trust, improving both accuracy and readability. Python code, descriptive quantity names. Use descriptive variable names in engineering calculations to make quantities clear, including their context and units. Clear naming helps reviewers understand the work and reduces errors during revision. The bridge dimensions are defined using clear, descriptive measurements. The deck width is 12 meters, the span length is 30 meters, and the concrete thickness is 0.25 meters. Naming these values clearly helps readers understand the physical dimensions used in later engineering calculations. To estimate concrete for a bridge deck, first find the deck area by multiplying its width by its span length. Then multiply that area by the concrete thickness to get the required concrete volume. Clear, descriptive naming helps keep these engineering calculations understandable and less prone to error. The bridge load calculation begins with a service dead load of 850 kilonewtons, representing the bridge's constant self-weight, and a service live load of 420 kilonewtons from traffic and other temporary effects. A dead load factor of 1.2 is also used as a safety multiplier to account for uncertainty. Together, these values support the safe calculation of the total load the bridge must carry. Set the live load factor to 1.6 to account for uncertainty in live load estimates. Then, multiply the service dead load and service live load by their respective load factors to obtain the factored dead and live loads. These adjusted loads include safety margins for design. Calculate the total factored load by adding the factored dead load and factored live load. Then find the average factored pressure by dividing that load by the bridge deck plan area. This gives the average pressure on the deck, which is needed to assess structural integrity. The output gives a concise summary of the main engineering results: bridge deck area in square meters, concrete volume in cubic meters, total factored load in kilonewtons, and average factored pressure in kilopascals. Each value is rounded to 2 decimal places for clarity. This script summarizes key bridge deck design metrics. It calculates the deck area and concrete volume from the given dimensions, applies factors to the dead and live loads, and combines them to find the total factored load. It then divides that load by the deck area to estimate the average factored pressure. The printed results give a concise overview of the deck's main structural quantities. Engineering expressions. Arithmetic expressions. Arithmetic expressions help civil engineers turn raw data into useful results, such as loads, volumes, and costs. Operations like addition, subtraction, multiplication, division, and exponents support common calculations for structures and materials. When these expressions are organized carefully, they make engineering work more consistent and meaningful than simple calculation alone. Order of operations is essential in engineering because small changes in grouping can produce very different results. Parentheses make the intended grouping clear, such as combining loads before distributing them, or finding an average area before calculating excavation volume. Clear arithmetic expressions improve accuracy and communication, helping prevent professional errors. Engineering arithmetic expressions should be checked for scale, realism, and physical meaning, not just computed correctly. Because the numbers represent real quantities like lengths, loads, or costs, results should match engineering judgment. If an answer seems unrealistic, the problem may be an incorrect dimension, a repeated multiplier, or another setup error. Treat each expression as a meaningful statement and make sure every part supports the design or analysis goal. Python code, arithmetic expressions. Arithmetic expressions are used to calculate engineering quantities. Use parentheses to make the calculation clear, and always check the units after computing. The beam is defined with a dead load of 42 kilonewtons, a live load of 28 kilonewtons, and a length of 7 meters. These values represent the constant load, variable load, and span needed to determine how the load is distributed along the beam. To find the distributed load on a beam, first add the dead load and live load to get the total load in kilonewtons. Then divide that total by the beam length to find the load per meter. This gives a clear value for the load distribution used in engineering analysis. The slab dimensions are set as 30 feet long, 18 feet wide, and 0.5 feet thick. These values are then used to find the slab's volume by multiplying the length, width, and thickness. Find the slab's volume by multiplying its length, width, and thickness to get cubic feet. Then divide by 27 to convert the result to cubic yards, the standard unit often used in construction. The circular footing has a radius of 1.2 meters. Its area is found by multiplying pi by the radius squared, giving the circle area needed to assess the footing's load-bearing capacity. The column load is set at 950 kilonewtons, representing the total force from the column. The bearing pressure is then found by dividing this load by the footing area in square meters, giving the pressure the footing must safely support. The script prints a concise summary of the beam and footing calculations. It reports the total beam load, line load, concrete volume in cubic yards, footing area, and bearing pressure. Each value is rounded appropriately and shown with its engineering units for clear interpretation. The script computes key structural quantities for basic load and dimension checks. It combines dead and live loads to find a beam's total load, divides by beam length to get line load, calculates concrete slab volume in cubic yards, and finds circular footing area and bearing pressure from the column load. It then prints the rounded results for clarity. Built-in functions. Python's built-in functions help engineers turn calculations into clear, repeatable results. They make common tasks faster, such as rounding quantities or finding maximum load effects, and are especially useful in civil engineering, where dimensions, loads, and costs are evaluated often. Built-in functions help engineers present numerical results clearly and with appropriate precision. Rounding, finding differences, and summarizing data make calculations easier to interpret and help avoid false precision. By matching the level of detail to the situation, these functions support clearer decisions and reduce misunderstandings. To use built-in functions well, engineers must know what inputs they expect and what outputs they produce. This matters in civil engineering because quantities like length, area, and force have specific meanings and units. Functions can speed up calculations, but results are only useful when the data is consistent, the units match, and the output is interpreted in the right engineering context. Python code. Built-in functions. Built-in functions help engineers check expressions and summarize calculated values efficiently. In civil engineering work, using meaningful variables also makes calculations easier to read and understand. The concrete footing is defined by its main dimensions in meters, a length of 3.6, a width of 2.4, and a depth of 0.55. These measurements will be used to calculate the required concrete volume. To find the concrete needed, multiply the footing's length, width, and depth to get the volume in cubic meters. Then round the result to 2 decimal places for a clear report-ready value. Trial beam reactions are stored as a list of forces in kilonewtons. The maximum value identifies the governing reaction, which is most important for safety and design, while the minimum value shows the smallest reaction and helps define the overall range considered in the analysis. The allowable settlement is 25 millimeters, while the predicted settlement is 31.4 millimeters. The excess settlement is found by taking the absolute difference between these values, giving the amount by which the prediction exceeds the limit. A list stores the inspection deflection measurements in millimeters. The total number of readings is found by checking the list length, and the average deflection is calculated by adding the measurements and dividing by that count. This keeps the calculation accurate, even if the number of measurements changes. The output summarizes key footing and inspection results, the rounded concrete volume in cubic meters, the maximum and minimum trial beam reactions in kilonewtons, the absolute difference between predicted and allowable settlement in millimeters, and the average measured deflection rounded to 2 decimal places. This Python script uses built-in functions to summarize key engineering calculations. It rounds the required concrete volume for a footing, finds the maximum and minimum beam reactions, measures the absolute settlement difference, and computes the average deflection from inspection readings. It then prints these results with appropriate units. Unit conversions. Unit conversions are essential in engineering because measurements and calculation tools often use different unit systems. They are part of the calculation process, not just a clerical step. And arithmetic expressions help apply conversion factors correctly. In civil engineering, small unit mistakes can cause serious practical problems, such as incorrect material quantities or misjudged structural loads. Unit conversions depend on what the measurement represents. Length, area, and volume each require different treatment, such as converting 1 dimension for a beam, 2 dimensions for a floor area, or 3-dimensional volume for concrete. Clear arithmetic expressions help apply the correct conversion factors, while built-in functions can support tasks like rounding values or comparing elevations in engineering calculations. Effective unit conversion requires both accurate arithmetic and a quick reality check. After converting, make sure the result fits the physical situation, such as realistic room dimensions or a reasonable road slope. Clear calculations help prevent mistakes, like using the wrong direction or applying a factor more than once, turning raw measurements into usable values. Python code, unit conversions. Unit conversions make engineering calculations clearer and more reliable. Variables should identify both the quantity and its units, while built-in tools can help present results in an understandable way. Field measurements are stored with clear, descriptive names that include their units and meaning. The examples include a mile-long road length in feet, a beam depth in inches, and a concrete volume in cubic yards. This naming approach makes the code easier to understand and maintain. Define unit conversion factors as named values to make engineering code clearer and easier to maintain. Common factors include converting feet to meters, inches to millimeters, and cubic yards to cubic meters. Keeping these values explicit helps ensure measurements are transformed accurately between unit systems. Convert each measurement by multiplying it by the appropriate metric conversion factor. Road length changes from feet to meters, beam depth from inches to millimeters, and concrete volume from cubic yards to cubic meters. Round the road length to 1 decimal place and the concrete volume to 2 decimal places to make the results clear and suitably precise. Then compare the road length, beam depth, and concrete volume to identify the largest converted measurement and get a quick sense of their relative scale. The output reports several converted measurement results with appropriate formatting. Road length in meters rounded to 1 decimal place, beam depth in millimeters shown directly, and concrete volume in cubic meters rounded to 2 decimal places. It also prints the largest converted numeric value rounded to 1 decimal place, then confirms the data type of the road length value for verification. This script converts common engineering measurements from imperial to metric units, including length, depth, and volume. It uses fixed conversion factors, rounds the results for readability, and prints the converted values in meters, millimeters, and cubic meters. It also reports the largest converted number and confirms the data type of the road length result, providing a clear metric summary of the measurements. Built-in functions. Rounding results. Rounding in engineering makes measurements and calculation results easier to read and appropriate for practical decisions. In Python, it controls how floating point numbers are displayed, but rounded values can affect later calculations if they are reused. The key is to match the number of decimal places to the needed precision, such as an order form, measuring tool, or engineering standard. When doing calculations, keep a clear distinction between rounding for display and rounding for later use. Display rounding only changes what is shown, while using rounded values in later steps can let small errors accumulate. In fields like civil engineering, this can affect material estimates, so it is best to keep full precision during the work and round only the final result to the required number of decimal places. Rounding a number does not always make it behave like a whole number, especially if it remains a floating point value. When a result represents a count, such as trucks or materials, it may need both the right numeric type and the right rounding direction. Choose rounding methods based on the practical context, so calculations stay reliable and meaningful. Python code. Rounding results. Rounding helps make engineering results easier to communicate, but floating point values should be handled with care. Keep as much precision as possible during calculations, and round only when presenting the final result. The concrete slab dimensions are defined in meters: a length of 12.4, a width of 7.8, and a thickness of 0.18. These values are stored as floating point numbers to keep the measurements precise for later calculations. Calculate the slab volume by multiplying its length, width, and thickness using full floating point precision. Then round the result to 2 decimal places so it is easier to read and report while keeping reasonable accuracy. Set the number of bays to 20, then calculate the total slab volume in 2 ways. First, multiply the precise volume per slab by 20 to get the unrounded total. Then multiply the rounded volume per slab by 20 to see how rounding before multiplication changes the final result. The code first displays the slab volume before rounding, along with its data type, to confirm the calculated float value. It then shows the rounded volume, demonstrating that rounding changes the displayed number, but not the float type. Finally, it computes the total volume for all bays and prints it rounded to 2 decimal places, with cubic meters as the unit, making the result clear and suitable for reporting. First, compare the total volume found after rounding values before multiplication with the total found using full precision. The difference between them shows how early rounding can change cumulative results, which is important for understanding possible discrepancies in engineering calculations. The truck capacity is set to 6 cubic meters. Then the total volume is divided by that capacity to estimate the required number of truckloads. The result may be a decimal, so it is rounded to the nearest whole number before printing. However, rounding can underestimate the need because a partial truckload may still require an additional truck. This script shows how rounding affects engineering calculations. It computes a concrete slab volume precisely, then rounds it for readability, and compares totals based on the precise versus rounded value. The example shows that rounding too early can change the final volume, and that rounding truckloads to a whole number can underestimate what is actually needed. The main lesson is that rounding improves clarity, but it can also affect accuracy and practical decisions. Absolute values. Absolute value is important in numerical computing because it shows a number's size without its sign. In engineering, signs may represent direction, but the magnitude of an error or difference is often what matters most. Using absolute value turns signed results into non-negative values on the same scale, making calculations clearer and reducing the risk of misreading negative values as less important. Absolute value changes only the sign of a number, not its type or precision. Whole number differences remain whole numbers, while decimal values should keep their decimal precision. This matters because decimals, such as survey elevations, can reveal small errors that rounding might hide, while counts naturally stay as whole numbers. Absolute values are useful in engineering because they show the size of a deviation or error, regardless of direction. This helps with tasks such as checking construction tolerances, judging structural model accuracy, and calibrating environmental models using residuals. However, when the direction of a difference matters, the original sign must be kept to preserve the correct context. Python code. Absolute values. Absolute value shows size without direction, but in civil contexts, positive and negative signs can carry important meaning. Being aware of the quantity type helps avoid hidden calculation errors. The predicted beam deflection is 0.42 inches, while the measured deflection is negative 0.48 inches, meaning the beam moved in the opposite direction. The signed error is found by subtracting the prediction from the measurement, giving a difference that reflects both the size and direction of the error. Use the absolute value function to find the magnitude of the signed error, removing whether it is positive or negative. Then, compare the original signed error in inches with the absolute error in inches, so you can see both the direction of the error and its size. Set the design elevation to 102.75 meters and the surveyed elevation to 102.68 meters. Subtract the design value from the surveyed value to find the elevation difference. This difference shows how the actual measurement compares with the planned elevation. Calculate the absolute elevation difference to get its size regardless of direction. Then display the result in meters and confirm that it is still afloat, so the decimal precision is preserved. The order called for 120 bolts, but only 116 were delivered. By comparing these amounts, we find that 4 bolts are missing, and this missing amount is recorded as the bolt count difference. Calculate the absolute difference between the bolts delivered and the bolts ordered to find the size of the discrepancy, whether bolts are missing or extra. Then display that quantity and check its type to confirm the result is still an integer. A thickness error of -0.35 centimeters is compared with an allowed tolerance of 0.50 centimeters. By checking whether the error's absolute value is within that limit, we determine that the thickness deviation is acceptable. The code reports whether the thickness error is within the allowed tolerance. It does this by using a previously calculated true or false result that checks whether the absolute error is no greater than the tolerance, then prints that result to show if the thickness is acceptable. This script shows how absolute values help measure error sizes in civil engineering calculations. It compares predicted and measured beam deflections, design and survey elevations, bolt quantities, and thickness tolerance by separating sign differences from their magnitudes. The key idea is that signed values show direction, while absolute values show size, helping prevent mistakes when checking errors, quantities, and tolerances. Type checks. Type checks help ensure that values from sources like keyboard input or files are suitable for the calculations you want to perform. In Python, every value has a type, which determines how it can be used. Measurements should be stored as numbers, while labels should remain text. Checking types helps prevent failed or unreliable calculations, especially in engineering work where accuracy matters. Type checking helps ensure that data is used correctly in engineering calculations. Numbers such as pavement thickness or material density must be treated as numeric values, while project codes and comments belong as text. If a number is stored as text, calculations like concrete volume estimates may fail or give unreliable results. Checking types early helps catch these hidden mistakes and confirms that key assumptions are valid. Engineers need to distinguish integers from floating point numbers because whole counts and decimal measurements must be handled differently. Checking data types helps confirm that values are being used correctly and can reveal problems such as import mistakes or conversion errors. Regular type checks support more accurate, reliable calculations and better debugging habits. Python code type checks. Type checks help keep engineering calculations safe by making sure values are used in appropriate ways. Even when values appear similar, their Python types can determine which operations are valid and prevent misleading results. This example shows how common engineering data can be stored using different data types. A span measurement uses a decimal value. A pile quantity uses a whole number, and a beam identifier uses text. Together, they illustrate how numerical and labeled data can represent civil engineering information. We check each variable's type to confirm it is being used appropriately. The span value is a floating point number for real number calculations. The pile count is an integer for a whole number quantity, and the beam label is a string for text identification. A measurement imported as text is stored as the string 18.5. To check whether it can be used in arithmetic, the value is tested with the isInstance function to see if it is an integer or a float. The result is false, confirming that the value is still text and must be converted before doing calculations. Convert the thickness from text to a number so it can be used in calculations. With the area set to 42 square meters, find the volume by multiplying the area by the thickness, then dividing by 100 to convert centimeters to meters. The code first confirms that the converted thickness value is numeric, so it can be used in calculations, and prints whether that check succeeded. It then finds the concrete volume by multiplying the area by the thickness converted from centimeters to meters. The final volume is rounded to 2 decimal places and printed. The program verifies that the pile count is an integer, then prints the result of that check. It also confirms the system is ready for calculations only when the thickness value is numeric and the pile count is a whole number. This ensures that required inputs have valid types before any dependent calculations begin. This script shows how Python type checking helps make engineering calculations safer. It verifies that key values, such as a span, pile count, and beam label, have the expected number or text types before they are used. It also shows that a measurement imported as text must be converted to a float before arithmetic can be performed. After conversion, the script calculates concrete volume, rounds the result, and confirms the data is ready for further engineering calculations. In this lecture, you learn to create variables that represent civil engineering quantities with meaningful names, use arithmetic expressions and built-in functions to compute engineering values, and apply basic type awareness to avoid common calculation errors. In the next lecture, Lecture C, we will go over strings and input. Thank you for your attention. See you all in the next lecture.